Okay, let's talk about the three-dot problems from Chapter 5. There's two of them, one in each set. First one is problem 12, which basically has a puck being pulled by two forces. F1, which they tell you is a 7 Newton force horizontally, and F2, which they tell you is a 9 Newton force, and they are ambiguous about the direction in which it acts. So, whenever we're doing a force problem, we always want to start with a free body diagram. So here's my puck. Here is F1. Here is F2. I mean, F2 could literally be in any direction. I've got no clue. But I'm going to draw it in this direction at some angle theta and just kind of be content with that. Now, if you recall from concepts, our goal from here was to translate this into a statement about Newton's second law. And so this is still going to be true, but now it's going to be component-wise, just like we were doing with motion. So in the x direction, the net force will look like F1, whole thing, magnitude though, no arrow, plus F2, oof, that's an ugly cosine, cos theta, the x component of F2. In the y direction, it'll just look like F2 sine theta. They give you a graph of Vx versus t, and so they want you to kind of figure out what this angle is. And so, from the statement about the forces, we want to remember this, by Newton's second law, is going to be MAX. It'll be F1 plus F2 cos theta. So with this information, we can look at that velocity graph and maybe glean some insight from it, and then try to put this together. If we can figure out the mass, the acceleration, and we know these two forces, we can get the angle. This winds up not being super interesting. All right. The other three-dot problem is a significantly more aggravating three-dot problem. It's number 65. It's an Atwood machine. Atwood machine is basically just a pulley with two masses hanging off either side. They exist mostly to torment physics students. It's an Atwood machine, but it's a very special Atwood machine. One of the masses is leaking. And so it starts at a mass of 1.3 kilograms and is losing mass at a rate of 0.2 kilograms per second. So the first thing we really want to do here is try to write this, m1 as a function of time is going to look like 1.3 kilograms minus 0.2 t. I'm going to leave off the units because that's just going to be annoying otherwise. Try that again. Right? Now they want you to find information about the accelerations and such here. And so again, free body diagrams will be best cause of action. So we have, the weight on the first one, and then this tension in the rope. And then, I guess, we'll go with FT just to be consistent. And we have the weight of the second one, which is bigger, which is clearly indicated there, and again, the tension in the rope. Now, one thing to remember, since it's the same rope, it is the same tension. So that helps us. Another thing to be very careful about, though, whenever you have so this is kind of a Newton's third law problem because it's two objects interacting, although it's technically a rigid body. It's a weird mixing up of things. But the point is, we have to be consistent from setup to setup in terms of what direction is positive. So mass 1, since it's already lighter and is then just getting lighter as time goes on, is going to accelerate upwards. Mass 2, since it's heavier, is going to accelerate downwards. So I would recommend, as I look, I want to say, what is, for mass 1 and mass 2, F net, I'm going to say, is, for mass 1, the tension minus the weight. So I've made up the positive direction. Oh, incidentally, I should also point out, because it's a rigid body, kind of, these accelerations have to be the same. You can convince yourself of this by thinking what would happen if the accelerations were different. So stop, think on that for a second, and if that's not convincing you that they have to be the same, come talk to me. It's a weird thing. It feels like, after the fact, once you accept it, it kind of feels obvious, but it's not intuitive, I think, in most cases. Alright, so this is true. And then for the second mass, I'm going to make down positive. Now, switching, you can multiply an expression by -1, and that's effectively the difference between making down positive or up positive. The problem is that you have to make sure that you are consistent inside of each of the masses in terms of what direction you say is the positive direction. Because if you don't apply it consistently, so if you make the tension positive both times but down positive, but if you, no, that would still work, but just, it's a minus sign issue. It always kind of just makes me nervous. Anyway, once you get that kind of set up, there's calculus after this, so be careful. It does ask for kind of a maximization problem. Although, if you are exceptionally clever, you might see a way to avoid doing too much calculus. Right. Hopefully it's enough to get you started and give you some kind of direction there. As always, let me know if you got questions.